All right. Good evening, everyone. We'll be starting our workshop in a few more moments. All right. Okay, so let's begin. So, good evening. I'm Meng Wai Kit, a Microsoft Learn student ambassador. And today I'll be having this workshop to teach everyone about training diffusion models on Azure Machine Learning to produce art. So, our agenda for today will be about Azure Machine Learning and diffusion models. So, let's just start with Azure Machine Learning. But before we could do that, we need to understand what is Azure and what is machine learning separately first. So in this slide, you can see that Azure is a cloud computing platform that offers multiple solutions. And just to name a few, there are AI solutions for you to have pre-trained models, or for you to train your own AI models, or to use their cloud infrastructure to train. Aside from that, there's application development solutions so that you can collaborate and test your development of applications. Next, there are cloud migration and modernization services. So, if you were to have any infrastructure that you would like to have on the cloud instead, Azure also offers solutions like that. Aside from that, there are data and analytics for you to have business intelligence and for you to make decisions better in your business. And there's many more. As you can see, hybrid cloud infrastructure, Internet of Things, security and governance, industry solutions, and many more. So next, you can see, let's just give you a reminder or to those who do not understand what AI, ML, and DL is, a small introduction. Well, artificial intelligence is just a technique that enables computers to mimic human intelligence. For example, we can use artificial intelligence to create a machine to produce art just like how a human would. Um, Meanwhile, machine learning is a subset of AI that includes techniques that enables machines to improve tasks with experience. So what this machine learning allows us to do is that after creating a machine, right, that machine won't be able to to replicate human tasks that well. So via machine learning, we are able to gradually train and make the machine better at its job. Next, we have deep learning, which is a subset of machine learning that is based on neural networks. And what neural networks are is that the machine is built similarly or inspired in a way that is inspired by the human brain, where each neuron or node in the neural network is similar to how one neuron cell is in our brain. So this is just AI, ML, and DL. So how do we have a machine learning project, right? How do we build AIs and what are the steps involved? Well, as you can see from this slide, the first step is comes from our data sources. So to train an AI or to start a machine learning project, we would need a lot of data. For example, if we were to train an AI model to produce art, then we would need a lot of data of real life art, right? Next, we would have to build the model. There are two ways, as you can see over here, that we can build the model. The first way is to build via classical ML methods, for example, binary trees, binary forest, linear regression methods, and all that. Or we can use deep learning methods, which is the one that I've mentioned before, that has the model um, built in a way that is inspired by how the human brain works. And in this workshop, we will be going with deep learning, the deep learning model method. Next, we would have to tune the hyperparameters. And the way I would like to describe hyperparameters is that like hyperparameters are like settings, right? So we would have to tune these so-called settings such that we can optimize the training of the model. The settings include something like learning rate. So how fast does the machine learning model, how fast does the model learn? Or it can also be the batch size, meaning how many images does the um, model train in a batch, or it can also be the epoch, right? Or meaning how many times does the whole training process repeat, right, on the same AI model. So these hyperparameters, and I mean there are more hyperparameters that I haven't listed out, but these hyperparameters can be tuned to optimize the training. So the next step is to actually run the training process, right? And this running of the training process is called an experiment. So we first need to collect our data source, have our model built, tune the hyperparameters, and then we will be able to run the experiment. And once we have run the experiment, we would be able to produce an AI model. However, um, this AI model might not be optimized, right? It might not be the best AI model we can produce. So, to make it better, we would have to try different permutations of data. We have to try different permutations of AI model structures, and also we have to try different permutations of hyperparameters. But manually changing all these components, right, the data, the model, and the hyperparameters manually, it's going to be a bit more difficult or inconvenient, which is why we have pipelines. And as you can see, the step in the middle is experimentations and pipelines, right? So what pipelines allows us to do is that it gives us modular control over these components. Meaning if we have, I'm just going to simplify this a bit, but if we have three data sources A, B, C, we have three models A, B, C, and hyperparameters A, B, C. Pipelines allow us to swap those things in and out quickly and easily, such that we can run many permutations of many different types of components. And after running all of these experiments with all these different um, permutations, we will then be able to produce many models, right? And based on the output of these experiments, we will then be able to select the best model and deploy it. So in this example, maybe we have created an AI that generates art, right? So maybe we'll deploying it means that we will be putting it to use. So this AI that generates art may be deployed at an art gallery, perhaps. And after it's being deployed and being used, we move on to the next step, which is DevOps for data science. And in this last kind of like last step, uh, the operation side of the things will collect data, right? We'll collect data and feedback from either the users or the customers. And this information will be collected and pass it back to the development part of the team, as you can see with this arrow, which goes back to the building model side. And with this information, we will be able to build the model again and train the model again and deploy the model again so that the AI model is constantly improving, right? As it is being used. So that is pretty much how a machine learning project works. But how does Azure help us in this machine learning project? Well, then we will have to look at the next slide. So this is how the Microsoft Azure machine learning kind of environment looks like. As you can see, there's Microsoft Azure at the outermost layer. Then you have your subscription, which is your payment for this Microsoft Azure services. Then you have your resource groups, which are kind of like groups of related resources for a specific project, and workspaces. So in this case, we'll be looking at the Azure Machine Learning Workspace. However, just like their services, there are many types of different workspace. For example, maybe you would want to deploy a website, then there would be a workspace for that. Maybe you want to collect data, there will be another workspace for that. But since our focus is on Azure Machine Learning, I will just show the Azure Machine Learning Workspace over here. And in this Azure Machine Learning Workspace, you can see that we have 6 components over here, right, that I would like to bring your attention to. The first one is the compute. And what the compute does is that it is a virtual machine, right? It is a virtual machine that you will be using to run all of your code, run all of your experiments, and run all of your training. Next, we have the notebooks. And if you're familiar with Python or Jupyter notebooks, well, then this will be the place where you'll be writing and developing all your code and also documenting it. So, um, next we have pipelines, which is similar to what I've described before. It gives you the freedom to have modular control over your workflows for the data, for the models, and also for your hyperparameters. Next, we have the data section over here, which allows us to store our data that we would like to train the AI model on. And after that, we have experiments, which allow us to run the AI model training, and models, which is where we will be storing and looking at our models so that we can deploy them in the future. All right. So next, I will be giving an introduction on the Azure portal. So let's just move to this side over here. And this is how the Azure portal would look like, right? And if you haven't created an Azure account yet, I recommend you to do so. But if you don't have an Azure account, or if you are unable to create one, it's fine. You may download my repository and also use the code that allows you to run things locally. But either way, if you're following along, just click on create a resource, look for Azure Machine Learning, and click create. So right now we are going to create our Azure Machine Learning resource. And this Azure Machine Learning resource will belong to a resource group, right? But since we don't really have a resource group right now, we can create a new one and just call it anything. I'll just call it MLSA workshop over here. Next, you want to name this anything is fine. I'll just call it Diffusion because this is the AI model that we will be creating. But any name is okay too. And please select your region also. Since I'm in Southeast Asia, I'll just be going with Southeast Asia. And let's just click on the review and create button. And then just wait for it to load for a bit and we can create our resource. So this Azure Machine resource is pretty much going to be a group of or a collection of all of our materials needed for the machine learning project. Over here, you can see the deployment that is in progress. And let's just wait for a moment for the resource to be deployed. So after this, there will be a download button, not this one, but there will be another download button for us to download the configurations file. So this configurations.json file is important because it allows us to identify our workshop. And after downloading this configurations file, we will be able to run it with our code so that we can work with our Azure Machine Learning workspace either from the notebooks on Azure or on our local computer in Visual Studio Code. All right, so now that it's deployed, we can just go to resource. And this is the JSON file that I've been talking about. Just click on this download button and I'll just leave it here for now. So right now we want to go to the Launch Studio button over here. And we will be able to look at the Machine Learning Studio. And over here, you can look at the assets that I've been talking about, the data, components, pipelines, models, computes, etc. So right now, I would want you to go to the Notebooks tab, because this is where we'll be writing, not really writing, but more like looking at our code, right? And the reason why I'm not asking you guys to write the code is because, well, it would be much easier if you can just copy or clone my repository. And to do that, we would need to go click on this terminal over here. And you might notice that this terminal is currently empty, right? We can't run the terminal. This is because we don't have a compute yet. We don't have a virtual machine to run the terminal. So next step would be to create this compute over here. And you can set any name for this compute. I'm just going to name it notebook MLSA, right? Because it's going to be running our notebooks. And this virtual machine type, I would recommend you using the GPU, but if you have access to it. But if you're using a free account like me, then you most likely won't have access to a GPU. But that's fine. You may use the CPU over here and select the standard E4D as V4. Or anything that is that has a really large RAM and storage, right? And after that, we can click on review and create and create. And this is the part where it will take some time for us to create this compute. But once we have created this compute, we'll be able to access the terminal. And when we are able to access the terminal, we can load my repository, and then we will be able to go through the code and train the AI model. And since this is going to take some time, let me just proceed with my slides over here. So now that introduced you to the concept of Microsoft Azure machine learning and also how machine learning projects work, let's just move on to how the diffusion model works, right? How does the AI that we are going to build in this session work? So let's just go to the next slide. And over here you can see this is how a diffusion model works simply, right? In simple manner. So first we have a random noise, right? This random noise is pretty much like TV static. It doesn't have any meaning to it, right? And what the diffusion model does is that it slowly denoises the image bit by bit. So firstly, we have a random noise. We pass it through the diffusion model. We will denoise it a bit. Then after that, we will take this output, pass it through the diffusion model again, and then it will continue to denoise it. And we will keep on this, keep repeating this process of passing the image into the diffusion model. And eventually, the image will be denoised to the point where we have an AI generated image on the right? And you can see this image is it looks like there's a waterfall, there's a river, there's a mountain, and etc. Right? And most importantly, it's in the style of the ukiyo-e Japanese image art style, right? That is because we have trained the diffusion model on ukiyo-e style images. So, but to go into more detail, right? To make it more understandable, this is an analogy that I like to use. So, how the model works is similar to how a sculptor sculpts a sculpture. Sculptor sculpts a sculpture, right? First, we have a big piece of marble, and then the sculptor will chisel away at it, whittle away at it, and then it will produce a sculpture. Similarly, we have a piece of random noise. The diffusion model will slowly and steadily remove noise from the diffusion from the random noise, and then it will produce an image. And you might be asking, well, how does the AI model learn to denoise properly, right? Because it's quite um, unbelievable that something would be able to denoise a piece of random noise into an AI generated image. Well, to train it, we will have to train it by letting it practice on real life images, right? So we will have to take real life ukiyo-e style images, artificially add noise to it, and then train the diffusion model to remove the noise from these artificially distorted images, right? And to do that, well, first we have to collect images of real life art. For example, there's a data set you can download online, and there's a link that will be able to access on the chat box if um, my friend is able to submit it at the chat box. But either way, we will be working with this data set of real life images. As you can see over here, there's the image. The first image is a monkey trainer performing at nobleman's house, Ushiwaka Maru, training with the Tengu, and courtesan in training. And there's many more in this, many other images in this data set. And next step is that we have to artificially distort our images, right? To do that, we would need a noise scheduler. This noise scheduler artificially adds noise to our image, either from 0 to 1,000 times, right? And as you can see, we have 5 images over here. And if we were to add the noise 10 times, it will be slightly distorted. 50 times, it will be more distorted. 100 times, it will be even more distorted. Same with 200 times. And when we reach 800 times, the image will be so distorted that it is almost unrecognizable. However, of course, this is just for illustration, but realistically, the noise scheduler will add the noise a random amount of times from 0 to 1,000, right? So now we have a data set of the original images, the noise that we have added, and the noisy photos, right? The distorted photos. I'll just be referring them as noisy photos from now on. And I will be referring to the noise that we added as the actual noise, right? The actual noise that we have added. And one thing I want you to keep in mind is that if we have the original images and we add the actual noise like we did just now, we will be able to get a noisy image. However, this process is reversible, meaning if we have the noisy image and we were to subtract the actual noise that we have added just now, we will be able to restore this original image, right? Which is why we are able to train the AI, the diffusion model to denoise images. But all right, so before we move on, I will have to, kind of tell you guys about a small little lie that I had to tell you to make the explanation easier early on. So I said that the noisy images will be entered into the diffusion model, and and we will train the diffusion model to kind of restore the original images, correct? But the thing is that that is not entirely true, right? The process is a little bit more complicated than that. So what actually happens is that when we take the noisy images and we insert it into the diffusion model, it won't produce the original image immediately. Instead, what the diffusion model will do is that it will try to guess what was the noise that we added onto this noisy image. This guess, I will call it the output noise, right? And if the output noise is similar to the actual noise that we have added, if we were to take this noisy image and subtract the output noise, then we will be able to restore the original image. So, to reiterate, its diffusion model doesn't immediately denoise the photo. Instead, it tries to guess whatever noise we have added. And if the guess is good, is accurate, then we will be able to restore the image via subtraction. All right, so moving on. We have to be aware that at the start, right, the diffusion model will not be able to predict the output noise very accurately, meaning the output noise will not be similar to the actual noise, right? Meaning, if we were to take this output noise at the start of this training process and subtract it from the noisy image, we will not be able to produce or restore the original image, right? Because the diffusion model is new, right? It's not trained yet. So, how does the diffusion model learn from this mistake? Well, in this next slide, I will explain how it does exactly that. So, like I said, its mistake is that it didn't produce an output noise that is similar to the actual noise. So, the way we train it is by calculating its error. So, to calculate this error, we will have to calculate the differences between the output noise and the actual noise. And this error or this calculated error is called a loss. Upon getting this loss, we will pass this loss into the diffusion model, and via a process called backpropagation, the diffusion model is able to improve itself. And the way backpropagation works is that it will take this number, all right, this loss, and then it will adjust its weights and biases, right? And once it gets a bit better, right? It still might not be able to produce the output noise accurately, right? Because training the diffusion model is going to take a lot of time and a lot of processing power, right? So even the second time, right, it might not be able to produce an accurate output noise, but it's okay because again, we will calculate the loss again and pass it through the diffusion model again, and via backpropagation, it will be able to improve itself even more, right? And we will keep on repeating and repeating and repeating this process. And eventually, right, when we take a noisy image and pass it through the diffusion model, it'll be producing an output noise that is somewhat close to the actual noise. And since the output noise is actually within the ballpark of the actual noise already, if you were to take the noisy image and subtract it with the output noise, then we will be able to produce or recover the original image um, more accurately, right? Meaning that the output image that we restore is just going to be slightly distorted. Of course, it is not possible to restore the image fully, but this is pretty much good enough, right? And it is at this stage that we can say that the diffusion model has an image or like an understanding of what ukiyo-e style images look like now, right? Because it is able to restore the image quite accurately, right? Okay, so going to the next step. Since the diffusion model has that understanding, we are able to produce images now, right? And remember how I said that the diffusion model denoises the random noise into original images, right? And remember also how I said that the diffusion model actually predicts the noise instead of denoising it immediately. Well, turns out the way it generates images is also um, more complicated, right? But it's fine. I'll just go through the process real quick. So over here, you can see this next slide, how the diffusion model produces image, right? The first step is that we have to input random noise into the diffusion model, right? That part doesn't change. But what changes is that instead of producing the slightly denoised image immediately, what the diffusion model does is that it predicts output noise again. But this output noise is just its own original idea of what it should remove to produce ukiyo-e style images. Because this random noise is just random. There is no underlying ukiyo-e style images for it to guess, right? So this output noise is its own original idea based on its own understanding of what ukiyo-e style images look like based on its training. And of course, um, we will take this random noise and subtract the output noise to get a slightly denoised image. And notice that instead of subtracting the entire output noise, we only subtract a partial of the output noise to get a slightly denoised image. And the reason for that is because we want to produce a great result, right? And if you were to take a random noise and subtract it out from the output noise immediately, right? If you were to subtract all of the noise in the first go, the output noise wouldn't be as good, and the output image wouldn't be as good. And the way that I would describe it is going back to our sculpting example, right? Imagine we have a big block of marble and the sculpture just gives it a few whacks. Of course, the image or the sculpture won't be as good, right? Because how can you could produce something of quality with just a few hits with a chisel? You'd have to hit it a few times and then look at it again, and then hit it a few times and then look at it again, right? So, just like a sculpture, the diffusion model works in somewhat of a small similar way, right? So once we have gotten this slightly denoised image, which is like kind of like a draft, we'll pass this slightly denoised image back into the diffusion model. And the diffusion model will produce another output noise, right? Which is the next analysis of what step we should do. And then we will take this slightly denoised image and subtract it with a partial of the output noise to get an even more denoised image. And of course, we will pass it through multiple times. And um, eventually, this the, when we pass this even more denoised image into the diffusion model, and it will produce again another output noise. And once we denoise the image one final step, then we will be able to get an AI generated ukiyo-e style image, right? So this is how the diffusion model um, generates images by predicting the output noise, and which is pretty much what it should remove from the image to get an ukiyo-e style image. So in the next slide, pretty much what I've explained is how a diffusion model works. But I've just represented the diffusion model as like a black box, right? We don't really know what's going on inside the diffusion model, right? We just have one input go in and another input come out of it, right? So to give you a better idea of what the diffusion model looks like, you can see that the diffusion model actually looks like this, right? It has a U-net structure. So in this UNet structure, we have different blocks. On the left side, there are downsample blocks, and on the right side, there are upsample blocks. And in the middle, there are bridges from the corresponding downsample block with the corresponding upsample block of the same resolution. So what happens is that when we insert an image from the left side, the image will be downsampled. And as the image is being downsampled, we will be able to extract features, meaning we will be able to identify where things are in the image. And as we downsample the image, we get better features, but the resolution will be really bad, right? As you can see, we may go down all the way to 4 times 4 pixels, which is not a really high quality image. So to maintain this feature map while increasing the resolution back to the 128 times 128 pixel, we need to have the upsample blocks on the right side. But by increasing the resolution, we also lose the clarity in the features. And when because as you like, I'm sure you can imagine, right? If you have a 4 by 4 image and we just slide it up, right? We just expand it up, like drag it up into 128, the image will be very blurry. So to maintain the clarity, we will have to get information from the corresponding downsample block, which is what the bridges are which is what the bridges are in the middle, right? It allows us to get information from the left hand side to maintain the clarity of the features on the right hand side. And to give a little bit of visual aid as to what's going on, here is what it would look like, right? So first we have this images entering into the UNet structure. And as we downsample the image, you can see that the pixels are being more concentrated, right? This allows the AI model to know where things are more clearly, right? Or where things are more generally. And over here, the AI model is able to generate like a feature map, right? Which is its idea of the features of the image. This yellow outline over here. But if you were to take this image from this bottom right over here and drag it up to 128 times 128, it will be a very blurry feature, right? So as we increase the resolution, we get information from the downsample block to ensure that the edges are still clear, and we keep doing that and keep doing that until we get an accurate and clear feature map of 128 and 128 resolution. And once the diffusion model knows identifies the feature of the image very clearly, then it will know what to remove and replace with its guess of the noise, right? So now you can see this image. It identified the bed and the person beside the bed. So now the AI model is able to fill in the gaps of the features with the noise so that it can generate the output noise. So this is the diffusion model. Okay. So after this, I'm sure I've explained how does the diffusion model work and what does the diffusion model look like on the inside. So now we can go and look at the code to see how that is being implemented, right? So as you can see, the compute is finally being is being created. So now we can run this command on the terminal. And um, you can find this command in the chat box, right? When my friend has pasted it over there. And you can just paste it into the notebook. So please copy this code from the chat box over there that my friend has posted and run this command. Right, so moving on, if you were to refresh the notebooks, you can see that my repository has appeared over here with the code. And in this ukiyo-e file over here, you can see all of the images, right, from our data set. So these are real images of ukiyo-e style image arts. Of course, if you'd like to experiment with different types of images, you may also download them online via a link that my friend also will provide in the chat box. However, I recommend just starting out with the ukiyo-e style images and just following along with this workshop. And to those that do not have an Azure account, right, you may go to the same website over here, this HTTPS link to my repository, download it, and you can run this local bracketed local file over here on your local computer. But to those who are following along, you may click on this upload dataset file, right? Azure upload dataset. So what we will be doing here is uploading our data from this ukiyo-e file over here to our assets. As you can see, our assets are still empty. If you were to go to data stores and click on default, you can see that it's empty, right? So we need to upload our data over here with this code. So what you have to do is click on this kernel and change it to the 3.10-SDK v2. And for our code to access our workspace, we would have to upload our configuration file. And remember, the one that we download when we created the resource, we have to upload it right now. So you can go to downloads, click on this config.json file and upload it. Right. So this is the configuration file. All right, then now we are able to run the code. So firstly, we would have to get the directory of our dataset, right? And the directory is over here, ukiyo-e underscore e, underscore e. Over here, we will have to remove certain keywords from the images, right? This because the words like train, test, and valid will kind of like segregate our images. And the funny thing that I discovered while I was test running this workshop is some of the images have the word train inside. For example, one of the images that I showed you, for example, this one is called courtesan in training, right? So the thing that happened was that the word train in the title of the image caused it to be separated into a kind of like a training set, right? A different set when I was trying to load the images into the AI. So to prevent that from happening, let's just run this small little script to remove these three words from the file names. Okay. And next we will have to get our workspace. As you can see, with this code, we are getting our workspace from this configuration.json file. We can see that this is successful because we have already gotten our diffusion resource, Azure machine learning resource, Southeast Asia, under the MLSA workshop resource group, which is also in Southeast Asia, right? So next, we will have to get our default data store because remember, I was showing you that this data store is empty and this data store is the default one, right? So we'd have to access our default data store with this code, ws.getDefaultDataStore. Right. And now that we have gotten the access to our data store, we will now be able to upload the data from this ukiyo-e directory into our default data store with this code over here. All right. So the images are being uploaded, and you can see there are 1,169 images. If you have other images that are also ukiyo-e style related, then you may upload it to the dataset also. And if you were to refresh this page over here, you can see that we have this new folder that pops up with all of our images, right? Okay. So now that this is done, we can move on to the next slide, the next notebook. All right. So in this notebook, we will be using the diffusers, right? Diffusers is a is a sorry is a library but from Hugging Face that allows us to have access to data to different types of AI models, right? And to gain access to them, we have to install the necessary dependencies using this line of code. And of course, this may take some time. But once that is done, we can also proceed to install even more dependencies over here. And the one over here, right, it's Git LFS. So what Git LFS allows us to do is that it allows us to, while we are training our AI model, right, our diffusion model, we can upload it to a repository online. However, I'm not going to go into detail about that because I've disabled that feature. But you may experiment it if you want to do that. So next we'll have to install IPY widgets also. So IPY widgets allows us to have the interface, right? The web interface for our Hugging Face login later. Okay. As you can see, because we have IPY widgets, we have this interface popping up over here without issues. So what you want to do is you want to click Control and left click on this link. And hold on, yeah. And we'll be able to access the Hugging Face tokens. If you already have a Hugging Face account, this is what it will look like. But if you don't, please do create one and log into it. And when you have done that, you'll be able to access the tokens, right? Of course, if your account is still new, you probably don't have any tokens at all. So what you'd want to do is to click on the new token button and name it whatever you like. But since we are doing a diffusion model, I just named it diffusion, right? And you'd want the role of this token to be write instead of read. And then after that, you can click on generate a token. But since I already have a token over here, you can just copy the code and then you can not the code, the token, and then paste it over here and click login. So once you have logged in and the token is valid, then we will be able to proceed. So in this next section, we will be configuring our training, right? So remember the hyperparameters that I mentioned at the start? Well, this is where we will be setting most of them. So in this configuration part of the code, we can set the image size to 128, right? Which allows us to have the image input and output to be 128 times 128 pixels, and the batch size to be 16 and evaluation batch to be 16, right? The training batch size equals to 16 means that we will be training the AI using 16 images at once, right? At a time. And this evaluation batch size allows the AI to generate 16 images at a time when we want to evaluate it. The number of epochs equals to 50 means that we'll be repeating this training process 50 times. And this 3 lines of code over here is pretty much related to the learning rate, right? So we will be using a very low learning rate because instead of a very high learning rate, as you can see, the number here is e minus 4, right? It's a very small number. It's 0.003, A001, if I recall correctly. It is a small number because we want the AI, the diffusion model to learn slowly so that it doesn't overshot its convergence point. The convergence point being like the area of lowest error, right? So you want it to be as accurate as possible and not overshot the convergence point. Next, we have save image epochs and save model epochs set to 1 and 5. This pretty much means that every epoch we will want to save sample images, and every 5 epochs we will want to save a checkpoint of the model, right? And all right, and this output directory is pretty much just going to be the place where we will be saving our AI model and all our samples and also all of our logging. So next, oh yeah, and speaking of the push to hub, right? So this push to hub, I have set it to false because if you set it to true, you'll have to create a repository online so that we can save the model using Git LFS, which I mentioned briefly over here. But I already set it to false so that we don't really have to deal with that right now. So let's just run this configuration, just save it. And now we will have to load our data set from our default data store, right? So again, we will have to access our workspace, right? And to access the workspace, we'll have to access it via our configuration.json file again over here. As you can see, we have already accessed our workspace properly. And over here, we want to get our data from the data store and then mount it locally so that we can access it. So let's just run this code and go through it line by line. So over here, we have gain access to this default data store. And then from this default data store, we want to get data from this specific directory called this ukiyo-a directory over here. ukiyo-a directory. So once we have gotten the ukiyo-a directory from the data store, we want to mount it on this mounted path. This mounted path can be named anything. I just named it TMP for temporary and ukiyo-a, right? So this is a temporary directory that we have mounted the data set on. So next, we can load the images from our mounted path, right? All right, so over here in this line of code, just one line, we load the images from this mounted location directory and place it into our data set, this data set variable. So when we want to to modify and work with the images, we can now just access this data set variable over here. As you can see, there are 1,167 images. So this is going to take a little bit of time, but that's okay. All right, so once all of the images have been loaded into the data set, I can just quickly show you how the data set looks like right now. So you can see there are 1,167 images. All right, and to just let you see what the images look like, let me just use matplotlib and have a look at these sample images over here. So this is images that we have gotten from our data set. Our data set. All right. So one thing that you might notice is that the images have have different aspect ratios and resolutions, right? But we already said that we want the images to be 128 by 128. To do that, right, to change and transform the images, we will have to use Torch Vision to perform some transformations. So over here, we can resize the images to 128 based on our configuration that we set above. And then we want to randomly flip the images horizontally to give it some randomness. And then we want to convert the images to tensor and normalize the images, right? So what does this to tensor and normalize mean? So if you are aware, the images are stored as binary data, right? But the thing is that the AI model isn't able to exactly understand that form of the data. So to convert it into a form that it can understand, we have to convert it into an array-like structure, right? Also known as like a tensor. So this conversion of the image data into the tensors that the AI can understand will be done via this line of code over here, right? So without this, we won't be able to input the images immediately into the AI model. And what does this normalize mean? Well, this normalize allows us to change the pixel values from to in a range that goes from 0 to 1. Because what is going on here is that each pixel has an RGB value, right? Where the red color of the pixel can range from 0 to 255, blue can range from 0 to 255, and green from 0 to 255. Well, what we want to do is to constrict the values from 0 to 255 to 0 and 1. This is because, well, we just make the number smaller and make it easier for the AI model to be trained. So these are our transformations that we have to set. And once we have these transformations, we can apply it to all of the images. And let's just see what the images look like right now. All right, so you can see that they are all stretched to or compressed to a 128 resolution, and some of them are even flipped horizontally randomly, right? Yeah, I think this one is flipped, and this one also. Oh no, only the right one is flipped. Yeah. Okay, so now that we have transformed our image, then we can save that images from our data set into the data loader. So the data set is just a location for us to transform our image, whereas the data loader is a location, is a variable that allows us to load the data um, to the AI model. So it is already in this train data loader variable. So over here, you can see that we have to define the diffusion model next. These are the explanations provided with the code, but I've already explained it just now via my slides, so I won't go into so much detail now. Over here, we have to create the UNet, right? To create this UNet, we'll have to download diffusers first, which this is just to make sure that we have everything installed, right? And once that is done, we are able to create the UNet model over here. So you can see that it has the same downsampling blocks and upsampling blocks, right? Just like how the UNet we have drawn over here looks like. So once we have created the diffusion model, the UNet model, then we will be able to just double confirm to check the input and output sizes. So you can see that the input sizes is 13128, 13128. All right. So this 128 and 128 represents the height and width of the image, right? So we are going to take an input of 128 times 128 and an output of 128 times 128 pixels. And this tree over here refers to the fact that each pixel will have three RGB values, right? R, G, and B. And this one over here means that it's taking in one image at a time and producing out one image at a time. So, well, we pretty much achieved what we want to, right? The input and output size are correct. All right. So next, if you recall, we would have to create a noise scheduler. So the noise scheduler is the one that allows us to artificially add noise to our input images, right? Our data set. So to do that, this noise scheduler is called DDPM scheduler, also from diffusers from Hugging Face. And in this DDPM scheduler, we want to have a number train time steps of 1000, meaning that it can add noise from 0 to 1000 times. Of course, you can change this value, but 1000 has worked well for me, so I'm just going to stick with that. So next, we'll just demonstrate, right, how does the image look after it has been added with noise 50 times. And to do that, we will first have to create a random noise, right? This random noise, which is our actual noise that we have mentioned in the slide multiple times previously. And then once we have created this noise and added it to the added it using the noise scheduler, you can see that the image is more noisy than before. Right? Compare this with what we have over here. Right? It has extra noise. As you can see, there's like some specks over here. So next, you'd want to take this noisy image and insert it into the model, and also the how many time steps, right? 50, and ask it to predict the output noise, right? Not predict the noise. And after that, we want to take this predicted noise, also known as the output noise that I've explained in the slide, and compare it with the actual noise to calculate this loss. And well, just to show you what the loss would look like, let me just type this out. And you can see this is what the loss would look like that we will be passing into our model. But since this is just to give you a rough idea of what this noise scheduler does, um, and this is not the actual training yet, we will not be using this noise to go for backpropagation yet. So now we have the noise scheduler. We have to configure the learning rate, right? Optimizer is not found. All right. All right, it's okay. Perhaps there's something wrong with the diffuser's dataset over here. It's not dataset, the diffuser's library over here. So let's just install it again. All right. So clearly something is wrong over here, but it's fine. Let's just move on first, and let me explain about the next functions, right? So what happens here is that you'd want the diffusion model while it's training to create some sample images. So the way it creates sample images is by making a grid, right? A 4x4 grid. And after creating this grid, it wants to evaluate itself, right? So it will generate 16 images and insert these 16 images into the grid that we have created over here, and then save that those images into a directory that we can then view. Right, next we will have to install this accelerate library, and this is our main training loop over here. So this is what is going to happen in the training loop. So first we have to get the logging ready, right, to let us know what is happening while we are training. And then we need to prepare the optimizer, the model, and the data loader, and the learning rate scheduler. And then we will be able to start the training process. So there will be a progress bar that you'll be able to that allows you to track the training progress. And well, all right. So let's just see what happens over here. So firstly, we'll have to get a batch of clean images, right, from our data set. Then we will have to create a random noise, and then we'll have to add this random noise to the or clean images to generate noisy images. After that, we'll have to use these noisy images as input to the model and allow the model to predict what was the noise that we added. And then we use this predicted noise and compare it with the actual noise to produce the loss. And once you have this loss, we will be able to use backwards propagation to improve the model. So what I've explained is actually just happening within these three simple lines. Not yeah, and also here. So once that is done, the progress bar will be updated, and over here, after every epoch or so, we will perform the evaluate mod function, which allows us to save sample images, the one over here. And after that, we have the save model function, which allows us to save the model to a local directory over here. All right. So now we will be able to train the model. However, yeah, of course, the optimizer, there is something wrong with the optimizer over here. Of course, I will look into the code and see if there's any errors. But for now, let me just show you what my previous run of this looks like, right? Because even if I were to be able to run this training code over here, it will take a long time to train. Because keep in mind that we are still using a CPU virtual machine instead of a GPU virtual machine. So it's going to take a long time. And my previous run, if I remember correctly, took around a day and a half. And this is my previous run. You can see over here in this file over here. Here are the sample images, right? So in this first sample over here, it's at epoch number 10. So at epoch number 10, the AI model is not that, the diffusion model is not that good yet, right? So what it generates is not, I mean, doesn't look like anything at all. But in the next 10 epochs, it gets better. But of course, the images look nothing like ukiyo-e style images yet. But of course, you'll slowly get better and better. And over here, at least the images are starting to look a bit more pleasant, right? Compared to what was over here and here, right? The images are starting to look pleasant. And at the epoch number 40, well, everything looks a little bit more vibrant, a little bit more, like I said, pleasant. And over here at the last epoch, well, the images are more detailed, right? And of course, the images that we have generated are somewhat abstract, and also some are still unintelligible. So it is for you to decide which image that you want to use or to display. For example, I've chosen this image because it's the best one over here that has the landscape of a waterfall and also a river. And the reason why this diffusion model is only able to create abstract art is because in our data set, we have a lot of subjects, right? So not only do we have flowers, we have people, we have boats, we have the sun in the sky. We have a lot of different components inside our data set, right? So what is happening is that the AI model understand what the field of ukiyo-e style images, but it is unable to identify the specific objects because we have not labeled what each and every specific object is. However, if you want to make things simple and not have to look for data set and not have to label the items in the images properly, you can just work with simple data sets, right? To have structured output. For example, if I were to look for DDPM butterflies, which was what this model was originally used for, you can see that this hold on, yeah. This AI model was originally trained on images of butterflies, right? And since all of the butterflies look quite similar to one another, right? It has a similar structure. The only thing that is different is the color. The output of the diffusion model will be quite consistent also, right? It will look mostly like a butterfly. This is because our training set is all butterflies, which is why our output will be all butterflies. But since our training data set has a lot of different types of um, aspects to them, our output will be on the more abstract side. All right. So this is our diffusion model, and this is where you can access it, right? So these are just the sample images that the diffusion model has produced during its training. And over here in this UNet folder over here, once it's done with the training and all that, you can look at this save tensors file. right? Diffusion dot underscore PyTorch underscore model dot save tensors. So of course it doesn't have an image because it's just a binary file, but you can look up on how to load this dot save tensors file so that you can generate more images with it. And also you can look for ways to deploy it and look for ways to use it on a practical manner, right? Okay. So um, going back to our slides, so far I've taught you what diffusion models, do they work, how do they look like, and also what is the Azure machine learning website and the platform look like. So what can you do next? So what's next is that if you haven't trained the model, if you have followed the workshop and you have trained the model on Azure, right? You can try training on your local computer also. You may download my repository over here. Perhaps there's a link in the chat box also that leads to my repository, and you can load my um, download my code. And the specific file that you want to run is this file over here, this local one over here. And if there's time, which I think we do have time, I'll be able to demonstrate this file over here so that you can see how it will run locally. Next, you can download and train the model with different types of images. So in this Google Drive link over here that you might have access to also in the chat box, you can see that there will be a lot of different types of images too. For example, there will be high Renaissance photos, there will be photos of Impressionism, and well, I can just give you a quick look at it also over here. So I've downloaded the photos over here, and just to let you have a look, this is the ukiyo-e dataset that we have used just now. This is the Romanticism one, for example. See, there are a lot of images from that era that you can also train your AI model on. And well, many more, right? There's so many over here. So you may download it from this link and train the AI model with different types of art. Next, you can learn about submitting experiments and using pipelines, right? Because what we have done is just train the model on your notebooks, but we have not went into detail about running experiments and changing the data and changing the hyperparameters and changing the structure of the model modularly. So you may also look into that next. And aside from that, you can also learn to deploy the model on Azure ML or on any other location, right? So that it can perform its purpose. Okay, so these are things that you can explore next. And for the one over here, right? This download and train the model with other types of images. If you have access to the Google Drive for the workshop, there will be a prerequisites and follow along notes. So in that file, if you go all the way down, you will see the tutorial or step-by-step procedure for this over here also. And I think you will be able to look for the link to the prerequisite notes in the chat box also. It will be the Google Drive link for the Microsoft Learn Student Ambassador Workshop. Google Drive, yeah. Right, hold on. Yeah, let me just show. It will be this one. Yeah, most MLSA Workshop Drive. Just post it over here. Okay, no problem. So yeah, all right. So now that this is pretty much what I want to talk about. So we can move on to the Q&A session. If anybody has any questions, feel free to ask them in the chat box about what we have talked about today. And at the same time, if there are no questions, we can just have a short break over here before we explore a little bit more about, since we have so much extra time, right? We can see the local code also. All right. If there are no questions that anyone would like to ask, then that's fine. I'll keep the questions open throughout the workshop. And as for now, we can just proceed with um, since we have so much time, right? Proceed with how the code can be run locally. So this is for those who do not have an Azure account, right? I'll just demonstrate it quickly, right? So what you'd want to do is you'd want to open up Visual Studio Code. Oops, this is a different folder. What I want to open is over here. Yeah, here. Yeah, okay. So what you'd want to do is click on this local file over here. And then we'll pretty much be doing most of the things similarly, right? Uh, we will we'll have to install the dependencies first. Of course, you will need to download Python, right? And I have the latest version over here, 3.11.3. And you would also need the extensions, right? The Python extension, Pylons. So once we have downloaded the dependencies, we'll be able to log into Hugging Face again. Click on the tokens, copy the tokens, login. And well, Git LFS is not important, but it's fine. Again, set the configurations. And this time we have to load the data set, but we're not loading from our workspace anymore. We're just loading from our local directory, right? And our local directory and our directory will be this ukiyo file over here. However, if you want to try training with different images, you can just change this directory to where your other images are downloaded at. So over here, we can get our uh, directory. And after that, we want to load the images from that directory into the data set. And it's pretty much the same process, right? And after this, I'm loading. You can see that the data set now has 11687 images. I just show the images how it looks like over here. Okay. We can transform the images. See what they look like right now. Right, they are all 128 by 128 and flipped randomly and to tensors and also normalized. And then after that, we want to load our data set into this data loader so that the AI model can accept it. So again, next, we want to create the 2D model. And it's the same. We have the same down blocks and the up blocks, right? Down sampling and up sampling. Next, we have to double check the input size and the output size. And after that, we need the noise scheduler to apply noise to our image and then calculate the loss based on the model's prediction of what the noise was. Hold on here. Okay. Oh, so there's a question. All this modeling process can run with normal CPU, right? Do not need to get a GPU for this, I presume. Yeah, all these images, all this processing can be run with the CPU instead of a GPU. However, of course, a GPU or a TPU will be much faster. And thank you for that question. All right, so moving on, we can set up, and I hope that answers your question. If I have not, you may feel free to ask even further. All right, so next we'll have to set up the training with this optimizer over here and well, set the learning rate scheduler, create the functions to generate the sample images, and all right, get the code for the training loop. And all right, then we will be able to train the model. And okay, I'm a bit afraid to run this piece of code because right now I'm using my computer to hold the meeting. So if I were to run this code, the training will use up a lot of my resource, and I'm afraid that I will disappear from this meeting. So I'm not going to run this right now. Um, and maybe you can run this when your computer is not running anything else, right? Just to be safe. And I run this locally also, and it works, right? But I would much rather do this when I'm not when I don't exactly need the resources to for anything important, such as maintaining myself in this meeting. So I'm just gonna leave it at this, right? But you can run this code and see that the progress bar will pop up, and you'll be start to run the training process. And over here, this line of code over here will allow you to get the sample images or view the sample images. So this is how it would look like if you were to run the the code locally. And as for the learning rate scheduler error over there, this optimizer, I think what the problem might be is related to the dependencies, right? So perhaps you have installed the diffuser's dependency of 0.11.1. So maybe you'd have to run this code over here, which is percent pip install dash r dependencies dot text, right? Maybe that will solve that issue. However, I will try to update my repository so that the error is no longer there. So this is a demonstration of how to run this training locally. All right. So that's pretty much it for this workshop. And before we end things, I would like to just have a small little photo session so that we can have remembrance of what of this workshop, right? So if you'd like to, please turn on your camera, and we'll just have a photo session to which will be uploaded to the Google Drive, right? All right. Do you want to count down so that we can take the photo? All right. So 3, 2, 1, smile, and then we'll take the photo. All right. So thank you so much for attending this workshop. I have already taken the photo, and you may turn off your cameras now. All right. Okay. Hope that you guys have learned something from this workshop, and please do if you would like to, please keep up with me on my social media. Because who knows, maybe I might host another workshop in the future. But that's all for our session today. Hope everyone has learned something new, and thank you.
Thank you, Waki.
Welcome. and thank you for attending also.